Hello friends, let's start with the assignment 6, contour integration using Jordan's lemma. The example is, show that integration from negative infinity to positive infinity sin of x over x square plus 4x plus 5 dx is equal to negative pi over e sin of 2. Remember, whenever we are having sin of mx or cos of mx in the numerator, then I change this into e the power iota mz. So here in the numerator, if suppose I am having sin of mx, then this will be changed into e the power iota mz, so that I can apply the Euler's formula later. So here m is equal to 1. So just take m equal to 1. So the numerator will become minus infinity to infinity. Numerator will be e the power iota z. Very good. And the denominator will be, just replace x with z. This is how we create this function. So this is z square plus 4z plus 5. Along this contour C, going from negative r to positive r along real axis, where we take the function in terms of x when integration. Okay. Then it is followed by a semicircle tau in the upper half plane, and along this we will integrate the function with respect to z. Fine. Alright. So first what we have to do, we have to find out the poles of the function, right? For that, just take the denominator equal to 0 and get the value of z. Now here it is z square plus 4z plus 5. If we can't make the factors, then we just need to make the complete square. So how to complete square? Here I am having z square plus 4z. Can I write 4z as twice 2z plus 5 is equal to 0. Now for making the complete square, I will add, this is twice AB. If you take A to B as ZB is 2, then I'm having Z square over here. Just I need to add 2 square plus this is twice 2Z, and because I'm adding 2 square, so I have to subtract also 2 square plus 5 is equal to 0. So this is a square plus b square plus twice ab, which is nothing but z plus 2 whole square, and this is negative 4 plus 5, which will be plus 1. So this is how we can make a complete square. So I'm just writing this as, this implies this is z plus 2 whole square plus 1 is equal to 0. So from here, z plus 2 whole square, take this to the other side 1, which is negative 1 then, and this implies z is equal to negative 2 plus minus iota, because square root of negative 1 is iota. So z is equal to minus 2 plus minus iota. Now which of the pole lie inside the contour? One is minus 2 plus iota, the other is minus 2 minus iota. If we check minus 2 plus iota, this will lie here at this purple point, right? So this is minus 2 plus iota, and minus 2 minus iota will lie outside this contour somewhere over here, just the opposite, right? So I have to calculate the residue only for those poles which lie inside the contour. So take the value z equal to minus 2 plus iota only. Then calculating the residue of fz at minus 2 plus iota, the formula is e the power iota z, numerator as it is, and in the denominator we need to take the derivative of the denominator with respect to z at z equal to negative 2 plus iota. So the derivative will be 2z plus 4, and then put the value of z over here. So this is equal to e the power iota z over 2z plus 4, right? And at z equal to minus 2 plus iota. So this comes out to be e the power iota minus 2 plus iota over 2 into minus 2 plus iota plus 4. And finally, this is e the power negative 1 negative 2 iota over 2 iota. This is your residue, right? Third thing is, I have to use the Cauchys residue theorem now. Now, what is the Cauchy residue theorem? This is integration over whole contour fz dz is equal to 2 pi iota times the calculated residue. So just write this 2 pi iota and the residue which I have calculated, this is e the power negative 1 negative 2 iota over 2 iota. Fine. 2 iota will be cancelled out. So this is equal to pi e the power negative 2 iota over e, taking this e the power minus 1 to the denominator. Now fourth thing is, I have to use the Jordan's lemma. Before that, I need to split this contour along the real axis and along the tau, the semicircle. So along the, whenever I have to use the integration along the real axis, I have to write the function in terms of x, and along the contour I have to write the function in terms of z. Please do remember this. So this is equal to pi over e into e the power negative 2 iota, right? And now using the Jordan's lemma. Now when we use the Jordan's lemma, if we know that our function is meromorphic and tending to 0 as z tends to infinity, and yes, the function fz, what is that? This one, e the power iota z over z square plus 4z plus 5. This is tending to 0 as z tends to infinity, and it is also a meromorphic function. So, and this value always comes out to be 0. There is also a formula for this, and so many times I have written that formula. Always the value will comes out to be 0. You can watch the previous videos. I have written and explained the formula for this, how to calculate this value. So just go through that. And also you have to limit your r tends to infinity on using this Jordan's lemma, right? So limit r tends to infinity, integration along the contour tau fz dz, this is always comes out to be 0. So this is your Jordan's lemma. And then before using this equation, I have to mention r tends to infinity in 1, because Jordan's lemma needs r tends to infinity, the limit. So just take the limit, just put r tends to infinity in 1. We get, when r is tending to infinity, this will become negative infinity to positive infinity. And f of x, we are having e the power iota z, so I am writing e the power iota x over x square plus 4x plus 5 dx is equal to pi over e into e the power negative 2 iota. Now remember, I need sign in the numerator, right? So now I am going to use the Euler's formula for e the power iota x, and that is what? E the power iota x is cos of x plus iota sine of x. Now to get this sine of x, what I have to do? Should I equate the real parts or imaginary parts? Of course, I have to equate the imaginary parts in this equation. Let's take this as 2. Equating the imaginary parts, we get this sine of x over x cubed plus 4x plus 5 dx, right? Is it clear? Okay, before that you can put over here, just write instead of e the power iota x as cos of x plus iota sine of x. Now is it okay? Alright. So you are having the two terms, cos x over x cubed plus 4x plus 5 plus iota times sine x over x square plus 4x plus 5. Now when you equate the imaginary part, then you will get integration for sine x over x square plus 4x plus 5 dx is equal to, now what is this e the power negative 2i? This will be cos of x, which is negative 2, plus iota sine of negative 2, right? And I know that sine of negative 2 is negative sine 2. So this is cos of negative 2 minus iota sine of, 2. Fine. And when you equate the imaginary part, you just need to write this. So this is equal to negative sine of 2. Fine. With pi by e. So this is negative pi by e sine of 2. This is our result, the required one, right? And if you are having cos of x here in the question, then you will have to equate the real parts so that you get your cos x, right? Because I need sine x in the numerator, so I have to equate the imaginary part and get the required result, right? Okay. This is an exercise for you all. Show that integration negative infinity to infinity sine of x over x square minus 2x plus 5 dx, you have to show this to be equal to I over 2a square sine of 1. Again, you are having sine over here, m is equal to 1. You need to change the numerator into e the power iota z for fz function, right? And then you will get your poles as the hint is given over here. The poles should comes out to be z equal to 1 plus minus 2 iota, and yes, residue is also given over here. You just calculate and match the value. The residue of fz at z equal to 1 plus 2 iota, because this pole will lie inside the contour. This residue is e the power minus 2 plus iota over 4 iota, right? Then apply the Cauchy residue theorem, apply the Jordan's lemma, equate the imaginary parts and get your required result. Fine. So this is an exercise for you. Please complete this. Thank you so much for watching this video. Do like and subscribe for the latest videos. Thank you. God bless you all.